All right, folks, we're going to continue on with BAO and Reconstruction. We have Zach Slepian from Florida talking about endpoint statistics.
Yeah, thank you, Chink, and thank you, everyone, for having me here. It actually doesn't feel too far afield because, as many of you will know, I spent quite a bit of time here as a postdoc and then as my first year of a professorship at Florida. But now they really made me go there and start teaching and doing all the fun things that come with professorship, like grant writing. Anyone? So yeah, today, obviously I'm in the Reconstruction session, but I want to talk to you about an alternative to Reconstruction, which is, as some people have already mentioned, just measuring the full endpoint statistics. I'm not going to have too much time to go into the detailed disadvantages, advantages of that versus Reconstruction. I think my takeaway from it is we should do both. And if we get the same, sure. My takeaway on endpoint statistics versus Reconstruction is just we should do both. And if the answers agree, that's great. And if they don't agree, then that could be telling us there's a systematic or something we haven't understood about the modeling. But either outcome would be better than doing just one and taking the answer to the bank incorrectly. So this is work in collaboration with Bob Kahn, who's at Berkeley Lab, and I think in the audience too, and Dan Eisenstein, who I worked with for my PhD and continued working with afterwards. And yeah, basically, as I said, this is in the Reconstruction session, but really it's an alternative to Reconstruction. So before we get into the endpoint statistics, I just wanted to briefly advertise a couple of things. This is just a slide about what I'm doing and what my group is doing. So I actually think of myself as someone who does theory, algorithms, and data, and high performance computing is the bridge between these three things for me, because I'm interested in figuring out the signatures we want to search for, then developing the algorithms to actually search for them and figuring out how to run those on high performance computers. This one's actually up the hill. They're now replacing it with a more expensive and faster one. But you know, I asked them if I could have this one when they're done with it, but I haven't gotten an answer on that. Put in a good word, anyone at Berkeley Lab. And then I think, you know, I find data the most satisfying part of science, and I'll be talking a little bit more about the opportunities with that upcoming with DESI. And I should, of course, mention, as I said, I just started at University of Florida. That's what it looks like there 90% of the year. And basically, we're in growth mode now. We've actually done 5 tenure track hires in the past 2 years, myself included. We're doing one more this year. And I'm also personally hiring a postdoc and trying to build a group. So if you might be interested in that, or if you know a person who's applying to grad school who might be interested in that, please reach out. This telescope is the Gran Telescopo Canarias. It's a 10.2 meter telescope in the Canary Islands, the largest optical one in the world, and we have a membership in it. And I've actually started to use that, basically just doing a small program using it to obtain high redshift WISE spectra with Alex Królewski, who's a finishing grad student at Berkeley, who any of you should hire as a postdoc. I'd love to. And basically, he did this nice paper with Martin, Simone, and Eddie Schlafly on using OnWISE to do tomography of CMB lensing. And I won't go into details with that. Ask him if you're interested. But basically, they found that, you know, if you're doing CMB cross correlation and you need DNDZ, the number density of objects as a function of redshift, the limiting uncertainty here is that DNDZ is very uncertain at high redshift. So if we could get a representative spectroscopic sample of even a couple hundred objects with GTC to nail that uncertainty down, you could actually use it to unlock the potential of this far larger WISE survey, which actually has 500 million galaxies. So GTC is basically, think of it like Keck. It has similar capabilities. And we've actually been awarded some time to go and pursue some of these spectra, and hopefully that will strengthen the CMB cross correlation. So also, on the theme of other stuff that I'm doing that's sort of tangentially relevant both to endpoint functions and to large scale structure questions like BAO. Another project I've worked on in the numerical algorithm space is a rotation method for accelerating multiple spherical Bessel integrals against a numerical source function. So this is work in collaboration with Yin Li, who's in the audience, Marcel, who we just heard a great talk from, and Zvonimir Vla, who was at Berkeley for a number of years. And basically, when you're trying to do problems like the analytic covariance matrix template for the 2-point correlation function, you end up with integrals that look like this. You have a spherical Bessel times another spherical Bessel times the power spectrum. And you can even have a k-dependent weight. If you had n equals 1, that would actually be a gradient operator. If you had n equals -1, that's an inverse gradient. And you need to evaluate these if you want to get an analytic template for the covariance. And that's actually one piece of the BAO pipeline that we typically use. We use an analytic template for the covariance because it keeps things smooth and reduces the need for mock catalogs. So the trouble is these F tensors are not one-to-one. You've got two variables over here, an R and an R prime, but you're only integrating out over the K. So it seems like you can't do this with Fourier transforms because Fourier transforms want to take 1K to 1R or 1R to 1K. You can't do 1K to 2 different config space variables. So one would like to exploit FFTs, in particular this very nice FFT log algorithm that makes these multiplicative integrals convolutional. And this is an algorithm due to Hamilton, but really going back to the 70s, a transformation into log space by Seligman. But unfortunately, as I said, these are not one-to-one, so you can't obviously do this. So my idea was just, let's rotate from a 2D plane of R and R prime, or A and B in this picture, to the 1D diagonals, which are shown in blue and red here, that give you the difference and the sum of these frequencies, A and B in this, decomposition. Sorry, I replaced R and R prime with A and B. And, this is a picture, this is the math. This math just says when you multiply out, say, a J0 by a J0, you get a cosine of the sum of frequencies and a cosine of the difference. But now these cosines are one-dimensional in the sum and difference. So you can actually write this integral and this integral when you plug this in as 1D integrals, and you can do this with FFTs. So I won't go through the details. Suffice it to say that this is a test case we did that is actually more stringent than the power spectrum. It has sharper structure, so it's more challenging to do numerically. And you can basically see that for different values of A and B, the two free frequencies, we get just extremely good agreement with the naive method where you just do this as, a 2D grid problem where you go, over this grid in A and B. And the overall takeaway, really due to a really nice implementation by Yin of this that took him quite a while to kind of hone, is that we can actually do these integrals 1,000 to 3,000 times faster than the naive method where you just do a 2D kind of search. It is hard at higher L for technical reasons. Talk to me after if you're interested. And our code is public, so if you're interested in seeing how it works, go for it. Okay, so just one more advertisement on the subject of other numerical algorithm type work I'm doing. This is actually also with Alex Grolewski. In his spare time when he's not doing big data analyses, he's implementing, algorithms for me. Sorry, Martin, I borrowed him. Basically, when you want to calculate the density field variance at a given scale R, we all know it's this integral that has this 3J1 of KR over KR all squared times the power spectrum. And often in cosmology, we want to know when is this variance of order 1 or 1.686. And that defines a nonlinear scale R, and that's the scale where we say fluctuations have really become nonlinear. So the naive way to find that R would just be you do this integral for a number of different R, and you do a root find. You basically say, okay, I overshot here, let's go back a little. And that's inefficient because you're going to have to do of the order of 10 or 20 integrals with different R to do that root find. However, if you rewrite this formula in configuration space, this 3J1 over KR actually is just the overlap integral of two spheres. So it has a nice geometric formula given by the volume of a lens. And Dan Eisenstein pointed this out to me a number of years ago, and I just kind of was thinking about it. And I realized you could write down this sigma of R just as relatively simple integrals over weighted correlation functions on a compact domain from 0 out to 2R. So it turns out that the correlation function is very, very smooth from 0 out to 2R if R is like 8 megaparsecs, which is roughly the scale at which this becomes 1. So if you just fit this with a polynomial, and it's a low order polynomial, you can do these integrals analytically and solve for where this is 1 analytically, and just write down your answer as basically the cubic formula if you fit a cubic polynomial. And that means that once you have the fit coefficients for these correlation functions, you just have your answer. You don't need to do a numerical root find. So, details are in the paper. This is just some plots showing more details, which I'm going to move through in the interest of time. But the takeaway is that we can get 40 to 80 times faster than the naive method for doing this calculation. And again, our code is public on Alex's GitHub, which had a slightly too long address for this slide. So check it out if you're interested. But this is just, some other stuff I've been doing to try to kind of improve different aspects of the clustering pipeline that we might apply for surveys such as DESI. In particular, this nonlinear scale calculation is actually relevant anytime you want to do an MC-MC where you need something like a concentration mass relation. So it's not so relevant on BAO scales, but I think a lot of the things discussed yesterday regarding extracting information from smaller scales could benefit from ideas like this, where you're just finding ways to evaluate those predictions more quickly. Okay, so now I want to move to the main theme of the talk, which is really, what do we do with the coming deluge of galaxy data? So I don't need to remind anyone in this room, but I will because I like these pictures. SDSS had 1 million galaxies up to 2016. DESI will have 30 million galaxies and quasars over a 5-year period. SDSS took about 15 years. DESI will take 5 years. DESI has a factor of 30 more objects. So DESI is 90 times more efficient. That's because we have these robotic fiber positioners that can reposition the entire 5,000 fiber plate in 1 minute. And so basically you can be reconfiguring the plate as you move to the next pointing. DESI exposures will be of the order of 15 minutes. So this is a really negligible cost. And this is just a machine to make the largest 3D map of large scale structure that man has ever known. So that's what we're doing. I believe that data is actually starting to come in either now or in the next couple of months. And it's just going to be a tremendously exciting time. So the question is, what do we do with all that data? There are two sides of this. One is better modeling. People have said a lot in this workshop about better modeling, and obviously there's a great deal of potential there. But what I want to talk about today is just fuller non-parametric extraction of the information. How do you go from a galaxy density field to just the set of all of the translation and rotation invariant information that is in that field in a non-parametric way, where you're not assuming anything about the physics or the cosmology or the bias model or this or that. You're just saying, if I needed to encode all of the information that's translation and rotation invariant, how would I do that? Now, of course, that's an assumption too, but we do believe the laws of physics, just by virtue of being laws, should be the same over there as they are over here, and should look the same in that direction as they do in this. Of course, RSD break that. I have thoughts about that, but we don't have time for it today. So the basic program here is exploit the symmetry to integrate out the angular structure and record it in a compact basis. So that's what I'm going to show you. So for a Gaussian random field, we know that the 2-point function has all the information, but late-time galaxies are not a Gaussian random field because the matter field evolves under gravity, and galaxies don't trace the matter field with perfect fidelity. That's biasing. And so you generate a 3-point correlation function. It's the leading order statistic sensitive to information beyond the Gaussian random field. Galaxy clustering has one, and we can use it to sharpen the BAO standard ruler. In the interest of time, I'm going to go through these slides relatively quickly because I think many of you are aware of them, but the next couple slides are intended as motivation for why we want to go beyond a 2-point function by just basically presenting a case where we did go beyond 2-point and it worked. So Daniel Eisenstein and I, a few years ago, developed this new basis for the 3-point function called the multipole basis. And this basis basically takes the two side lengths and the internal angle of the triangle, expands in a Legendre series where you have radial coefficients times Legendre polynomials, and then you can plot the radial coefficients versus the two side lengths. Red is an excess of triangles, blue is a deficit. Here I've just shown the dipole, which is the cosine theta moment of this. And basically this is a nice way to just visualize the 3-point function. Even that I think was quite helpful because it turns out that once you visualize it, you can see there are features, which I'll give it away. These are BAO features. So this basis also helps the computation. 3-point function naively is extremely computationally expensive. This is just an example about having lunch with people, which you're probably all thinking about at this hour. That shows that, if you have 10 friends, choosing 2 to have lunch with gives you 90 lunches, but choosing 3 gives you 720 lunches. So you need to have 2 every day for a year. And basically for large n, the 3-point function scales as n cubed versus the 2-point function's n squared. And that should be enough to tell you why with 30 million galaxies, you're going to run into serious problems rather quickly. However, this multipole basis enabled Daniel and I to develop this n squared 3-point function algorithm where we basically sit on this red x point, which is one galaxy. we look at these two green guys, which are directions R1 hat and R2 hat around it, and we factorize this Legendre polynomial weight into spherical harmonics that each depend only on one direction. So this actually gives you an order n squared algorithm, because you can use this addition theorem to split the integral that I showed. You can take this integral, which appears to require you to look at R1 dot R2, and split it into two separate integrals over the two directions. And basically, if you have the spherical harmonic coefficients of the 3-point function, of the galaxy density around each point, you can assemble the 3-point function from that without ever looking at pairs around a point. So this is just a picture showing how that works, and it basically reduces the order of the algorithm by 1 power of n, so you get an n squared algorithm. You can even do this with Fourier transforms, because obtaining these spherical harmonic coefficients is actually a convolution, because you basically are sitting on every galaxy and integrating against the same weights. These weights are just the spherical harmonics. They're an orthogonal basis, so when you integrate against them, you get the coefficients. So Daniel and I had a short paper showing this, a longer paper explaining the larger multipole framework, and we implemented this. It was 500 times faster than a naive triplet count, and only 6 times slower than a 2-point function. And we were able to measure this BAO signature in the 3-point function for the first time, because we could do it with a large enough galaxy sample and go to large enough scales. And basically, using that, we made the first high significance detection of BAO in the 3-point function, and we're able to measure the distance to redshift 0.57 to 1.7% precision just using 3-point function, so no 2-point function at all. Now, to remind you, this sample of BOSS got roughly, I think, a 1.1-ish% measurement of the BAO scale from the 2-point function. So I would say the 3-point function on its own is comparable, but not, let's say, competitive. We're not advocating you replace 2-point function with this. We're just saying, why not take that additional information that's in the survey anyways, and all it requires is a little extra compute time. So this method has now been developed by Lado Samushia and his postdoc David Pearson. They did it in the bispectrum, and also these results have kind of gone into the compilation of Alam et al. One can also do anisotropic 3-point function. I mentioned RSD actually break the rotation symmetry. You can actually systematically build that in by taking mixed multipole moments, where instead of having just one L, you have an L and an L prime, because the two spherical harmonics can have different angular momentum indices. If you rotate so that your line of sight points to one of the galaxies that you're sitting on, and you expand around that galaxy and do the harmonic moments of the other two, then you actually have a rotating line of sight algorithm for the 3-point function. So this is somewhat robust to wide angle effects, which are probably small anyways. And basically, you can isolate the peculiar velocity information into unequal L couplings, because an isotropic field will never generate an L-L prime coupling in this basis. So this is a completely novel probe of RSD in the 3-point function, but it does parallel the way that that's been thought about in the 2-point function already. And I'm working to actually perform such an analysis on BOSS data, pending graduate students getting things done. We can also exploit high performance computing to do this. While I was a postdoc, we actually implemented this anisotropic version of the 3-point function on Cori, and achieved basically something like 9.1 peak petaflops, which was 80% of the theoretical peak for the instruction mix we needed. And basically, we were able to do the 3-point function for 2 billion halos in 20 minutes, which would mean you could do it in 3 days for the whole observable universe. So the only real point of this slide is that nothing further needs to be done on the compute side. We could already do this quickly for all the galaxies we'll ever have, using actually outdated computers at this point, because this was a few years ago. So I want to just dig into this performance breakdown briefly to show you where we're going. The calculation of the basically of the harmonic coefficients takes like 55% of the time. The KD tree search for the neighbors of one galaxy that you need to expand into harmonics around it takes another 22% of the time. So basically, overall, finding the galaxies around central you're going to use, and then getting the harmonic coefficients takes like 77% of the time. Now that's going to be important in where we're going. So where we're going is from 3 points to n points, and that's the work that I've been doing in the latter part of my postdoc and the first part of my time at UF. So this is just a kind of canned history of what has been done on endpoint function beyond 3 before. I'm going to skip it in the interest of time, but it's there. And if you're interested, I'm happy to go over history. This is just the Fourier version of that. And here's the basic idea. You can describe the clustering about each point, i.e. galaxy in your survey, using a rotation invariant basis. Angular momentum eigenfunctions are exactly what you want for that. The endpoint function estimated about a given point is just going to be the product of n-1 harmonic coefficients, one for each radial bin, because each of those harmonic coefficients will represent a field galaxy here. You don't need a harmonic coefficient for the central because you can put it at the origin. Each of these harmonic coefficients has its own orbital and spin angular momentum, and this operation to get these will scale as the number of radial bins times the number of allowed angular momentum combinations, but notably not the number of objects. That's the key. It doesn't scale as number of objects anymore, so you avoid this punishing scaling, where if you had a 4-point function, it could scale as number of galaxies to the 4th power if you did it the naive way. So isotropy about a given point, which is what you have in the absence of RSD, means that only certain angular momentum combinations are allowed. And basically, you can think about this and realize that you have to have total angular momentum 0, because if you didn't, that angular momentum would point in a certain direction, and that would be a preferred direction, so it would break isotropy. So this turns out to be the scalar mode of multipolar spherical harmonics to connect to a quantum mechanics language. You can use translation invariance to basically expand into allowed combinations of momenta about every point. Again, this is a convolution, so it can be done with Fourier transforms, just like the 3-point. And we can calculate the covariance. In the interest of time, I'm going to basically summarize this, but the point is the full Gaussian random field covariance can be calculated in terms of these correlation functions of at most 3 arguments. Those correlation functions can all be expanded into a basis of tripolar spherical harmonics times radial coefficients. So this y, l, l prime, l double prime is a tripolar harmonic. And basically, averaging over rotations will give you a momentum coupling rule on these coefficients of the correlation functions. And you can find these coupling rules using nuclear physics spin algebra stuff from the 60s, which my collaborator Bob Kahn actually turned up in the LBL library. And this is kind of the Bible of this. It was translated by the Israelis from, I think, Lithuanian for a US scientific program. And it's crazy awesome if you can understand it. So you basically get coupling diagrams that look like this. And it's basically just, 3J coefficients or Clebsch-Gordon symbols on total steroids. It's like, you saw coupling of 2 angular momenta in quantum mechanics as an undergrad and probably wanted to die. This is like, let's do 10. And it turns out it's actually not that hard if you know how to draw these diagrams. This diagram just shows L1 and L2 coupling into L12. And then if you want to couple this L12 into another one of these diagrams, you just need to tie them together and, track the signs, and you get things like this. And it basically just gives you amplitudes for these coefficients that you'll get of the covariance matrix. So basically, just wrapping up here, you can use all this angular momentum magic to write down a compact analytic expression for the covariance matrix of any endpoint function in the Gaussian random field limit. And that covariance will always have the form of these F-tensor coefficients of the tripolar harmonic expansion of the 2-point function times some angular momentum symbol. So basically, once you get these tensors, which are just an integral of the power spectrum against 3 spherical Bessel functions, you have everything you need to evaluate any endpoint function's covariance template. And these are very efficient to evaluate, and we already did it for the 3-point function analysis a few years ago, and you can really do it on your laptop. I mean, I did it on my laptop back then. My laptop might even be better now. So basically, to just wrap up with a summary, let's compute the endpoint functions for DESI. We have the data anyway, and the computational cost is now going to be feasible. In detail, the dominant cost, as I said, from the performance breakdown, 77% of the time is just getting the harmonic coefficients after you found the neighbors. So once you do a 3-point function, you actually can get the endpoint functions for greater than 3, essentially without any additional cost, because you already have the harmonic coefficients you need. You just make different combinations of them. And as I've said in the last little bit of this talk, we know how to get a template for the covariance matrix in the Gaussian random field limit. So at least on moderately large to large scales, we're not in the situation where we need to look at a huge amount of mock catalogs to do this. We actually have a smooth template that should therefore be invertible. So we know how to optimally weight the data. Edge correction for survey boundaries works similarly. I didn't show you, but it does. And future work that I'm pursuing with a graduate student is using machine learning to then compress whatever endpoint functions that we extract from this. Basically ask, okay, now that we've measured all the endpoint functions, which combinations of them are most sensitive to the cosmology that we care about? So thank you for the time. I'll stop there.
Questions?
Won't the survey geometry make the integrals like non-trivial?
You mean for the covariance matrix? Yeah, I think it could. I think you could probably imagine plugging it in some kind of empirical way where instead of doing the integral of the power spectrum to get these F tensors, you do the integral of the power spectrum convolved with the window function. And I think that would actually capture most of it. But I know you're doing a lot of analytic stuff with Roma.
It can be decoupled for like some, but maybe.
Yeah, so that would actually be super interesting to kind of take what you guys are doing for bispectrum and see if it can be promoted.
Other questions? Now let's thank the speaker again. Okay, so next we have Chirag Moody talking about FlowPM.
Hi, I'm Chirag. I'm a graduate student at UC Berkeley, and today I'll be talking about FlowPM, which are the particle mesh simulations we are building in TensorFlow. This is work with Francois and Urosh. So the plan of my talk is basically threefold. First, I'll use forward modeling approaches for reconstruction, and I'll discuss some applications to motivate these simulations. In the later part of my talk, I'll discuss these simulations.
Sorry.
Yep.
Speak a little longer too.
Sure. Okay. Right. So in the first part of my talk, I'll basically discuss forward modeling approaches to reconstruction to motivate these simulations. And in the second part of the talk, I'll discuss some details of how these are implemented and how we believe these can be useful for the future of spectroscopic surveys. I'll focus only on reconstruction, but the use case of these simulations go beyond simple reconstruction. One thing that you can use this for is simulation-based inference. I'll not touch upon that, but I think Andrew and Chang discussed that in detail yesterday. Right, so basically what I mean by forward model reconstruction is essentially you start with the initial conditions of the universe, you forward model with PM or other simulations to the final matter field, and then use a bias model or any other kind of model you're interested in to model whatever data you're observing. And then you compare the model data with the observations you have given a noise model to write down the posterior for the initial conditions. So in this case, if your noise model is Gaussian, you'll have a likelihood term like this, plus the Gaussian, you have the prior on the initial conditions is always Gaussian. Now, what you can do after this is you have two choices for either you can take the optimization route where you maximize the posterior of the initial conditions to get a map estimate plus do a Laplace approximation to get the errors, or you can go the sampling route in which you run a Monte Carlo or some other sampling algorithm to get samples of the initial conditions given such a posterior. The problem is that in either of these two cases, you're solving a very high dimensional problem because you're trying to either sample or reconstruct the entire initial field over the entire space. So for reasonable resolution, what you have is a multi-million parameters, and the only hope you have of doing optimization or sampling is to use gradient-based approaches. For example, Hamilton Monte Carlo or LBFGS or gradient descent. And to this end, what you need is essentially a differentiable forward model that you can take the derivatives of. So that's the entire motivation. And before discussing the simulations, just some applications which we have explored in recent past for forward modeling reconstruction. One thing you can obviously do is reconstruct the initial conditions. For this, the forward model that you can use can be the bias model, which Marcel discussed earlier today. Or you can, in our case, we used a simple neural network model to go from final matter field to the halos that we are observing. We showed that this has promises for BAO reconstruction. So what I'm showing here is the cross correlation between the reconstructed initial field and the true initial field along the line of sight and perpendicular to the line of sight for standard reconstruction, which is shown here in dashed lines, and our neural network reconstruction, which is shown here in solid lines. And you see that you gain a lot, especially along the line of sight direction. If you calculate Fisher information corresponding to the BAO measurements for this, you gain 30 to 60% perpendicular line of sight and 2 to 3 times along the line of sight. This is fairly optimistic because we use halo mass fields as our data, and we assume that we know the masses correctly. So some of this will reduce when you use realistic scatters, but it's still a big enough gain that you gain non-trivial amount at the end of the day. The reason you do so good in the line of sight direction is because in the forward model reconstruction, in addition to density, what you reconstruct is also the velocity field. So what I'm showing here is essentially the scatter plot between the reconstructed velocity at the center of mass of the halo and the halo velocity, which is the center of mass velocity of the halo. The scatter plot, the cross correlation on individual tracer basis is 90% for the reconstructed velocity field. And if you look at the true dark matter velocity field, the cross correlation is still like 94%. So you're doing almost as good as you can expect to do with a dark matter velocity field. So in addition to improving reconstruction, this has further applications. For example, you can use it to undo redshift space distortions, or you can like combine such a method with other velocity servers. You can use KSZ information to improve your reconstruction or do a joint reconstruction kind of thing. Or recently, people have used this to also get cosmological parameters such as F sigma 8. The other thing that you can do with forward model reconstruction is essentially reconstructing large scale modes. This is the slide that Marcel also showed today morning. The challenge here is for 21 centimeter intensity mapping surveys, you have very bright foregrounds. You have orders of magnitude bright foregrounds. And what that ends up doing is create a foreground wedge. So if you look at the Fourier plane here, these are the modes of the surveys. And this dotted line essentially shows the boundary of the foreground wedge. So everything below this line, you do not observe. And depending on whether you're optimistic or pessimistic, you have different wedge considerations. But the end result being that between redshift 2 and 6, you can lose somewhere between 20 to 80% of the observed modes completely. But because of the forward model reconstruction, what nonlinear evolution does is that it couples the large scale modes with the small scale modes. So you can essentially use the small scale information from here to reconstruct the large scales and the wedge that you otherwise do not see. So this is the result that we get essentially. Here I'm showing cross correlation between the true H1 true observed 21 centimeter field and the corrupted 21 and the observed 21 centimeter field, which does not have any large scale correlations. And even on intermediate scales, because of this wedge, you lose a lot of information. But with the reconstructed 21 centimeter field, you get almost 95% of the correlations back at redshift 4. This is super useful because then you can use these future surveys to do cross correlation analysis with things like photometric surveys like LSST and CMB lensing. And at the same time, as a byproduct, you also reconstruct the initial conditions. So you can use those to do a BAO analysis. So what I'm showing here is cross correlation between true initial field and the reconstructed initial field from our method and the reconstructed initial field from BAO. Again, along the line of sight and perpendicular. And you see that standard reconstruction does not reconstruct anything inside the wedge because it doesn't have that information in the observed field, while we are able to get like between 60 to 90%, depending on the redshift. Right. So there are obviously other applications, but in the interest of time, I'll move on to assumptions and challenges that generally go in any of this framework. So the first thing that this depends on is what is your forward model. Most of these studies use either simple neural network or a bias model as your forward model to observe these traces, but that has limited validity. So what I'm showing here is essentially how the bias model performs for 21 centimeter exercise. On large scales, you're good, but on small scale clustering, you start to lose information. So if you want to push to smaller scales in the future, you need better forward models for this. The second thing it all comes down to is essentially what is the likelihood that you use to compare your data with the observations. Most of the studies use diagonal Gaussian likelihood either in the Fourier space, something like this, or in the configuration space. So this is the likelihood we used for our halo mass fields, where you're just taking the difference of log masses predictions. makes a lot of assumptions, especially regarding the noise. So you are completely ignoring the correlations that you might have in your noise. You are ignoring this data and data dependence of your noise. For example, most of these models get the high mass halos more accurately than you get the low mass halos. So your noise kind of depends on those things. Uh, you ignore the stochasticity that you have in the observations. And all of this is without going to other tracers. Like these problems will probably be more severe if you are using other tracers such as Lyman alpha or weak lensing, because they are much more non-Gaussian than what we have right now. Right. One way to get rid of that, one way to counter that is to use probabilistic forward models, where instead of just learning the model that you observe, you also try to learn the likelihood of what you're seeing. This can easily be done with deep learning models nowadays. For example, some of the architectures that you can use are like mixture density network and pixel CNN. So very briefly, what a pixel CNN does is calculate the probability of an image given some latent underlying field. It writes down that probability as a product of conditionals, where the probability of every pixel basically depends only on the probability of the pixels coming before. So you are explicitly introducing correlations in your likelihood here. So you're no longer restricted to a diagonal likelihood. And when you combine it with mixture density networks, you can go beyond simple Gaussian models. You can use Gaussian mixtures or any other parametric likelihood that you're interested in. This is just showcasing, and then once you have a likelihood, you can also sample from it to generate mock models. So this is showing just a simple case of training a mixture density network to generate halo mass fields without any optimization. I literally took like a simple ResNet and trained it without any optimizations. So this is the truth. This is the sample that you generate from it. This is the cross correlation and transfer function between these two for different realizations. And it works much better than a simple bias model, as it should, given the complexity of this. Right. So the point of the talk so far was to basically convince you to answer this question with a yes, that do you need differentiable forward models, which probably, if it's better if they interface with deep learning models, so that if you want to do a reconstruction of this form, it can be done super easily and trivially, and you are no longer computationally limited. Because coding a differentiable forward model is hard, as Andrew yesterday pointed out, because you need to both code the forward process and the gradients for this. And if everyone does it, you're essentially just reinventing the wheel again and again. So to that end, we present FlowPM, which is the particle mesh simulations in an ML framework. You cannot see some of the code here, but this is the entire setup that you need to do to run a forward simulation. Essentially, you just generate, you import TensorFlow, you just generate the initial conditions. You can run a batch size, so you can generate multiple universes at the same time if you want. You feed it in the linear power spectrum to generate the initial conditions. You generate the initial LPT displacements, and then you just call the n-body algorithm, and then you paint the things on a grid with an interpolation scheme, and you just run the scheme. Given that it is in TensorFlow, the gradients are readily available, and more importantly, they are available with every component of the simulation, not necessarily only the initial conditions. So if you want to throw in a bias model or something and want gradients with respect to that, they can be good. They can also be achieved super trivially. And you can also open the box of n-body simulation and use gradients with respect to intermediate latent variables which can help you with the simulation-based inference. And of course, because it's in TensorFlow, you have deep interfacing with deep learning elements. To open what the numerical scheme that we have implemented so far is essentially just interpolate the particles on the grid with a CIC or some other scheme. Do FFTs to get the force on these grid points, interpolate the force back to positions, and then do a kick drift to update the momentum and displace the particles. This is basically the fast PM scheme that we've implemented so far. If that's not your favorite choice of simulation, we believe that this essentially covers all the operators that you need to run any other approximate scheme of simulations. Okay, this is the kicker. So this is essentially the entire code that you need to reconstruct the universe in this case. So what I've done here is essentially made my linear field a variable that I want to optimize over. This is then using this linear field, I do the n-body simulation. I put it on the grid and I compare the likelihood with the observed data. If you have a Gaussian likelihood, this is my prior term. I just add them to get the total loss, and then I can use the inbuilt TensorFlow optimizers to do the optimization and reconstruct the field. If you have a deep learning model like a mixture density network or a pixel CNN to do reconstruction, all you have to do is basically comment this line, uncomment this line, which takes your deep learning likelihood instead of the residual likelihood. This is just showing an example for the reconstruction here from dark matter, just a toy problem. So my data is essentially a five-step fast PM simulation to generate the dark matter field. And it took me 200 iterations with the gradient descent optimization, less than 3 minutes on a single GPU to get this. And it essentially reconstructs the field perfectly. And the small scale power is suppressed because of the noise that I've put in the data. Right. So far, so good. The things that I have talked about so far, so we have implementation of this working, which I just showed. But the thing is that it works on a single GPU so far. And a single GPU does not have enough memory to essentially support things that you are interested in, like the large scale inference. So this requires distributed machine learning framework, and that will involve going from data parallelism to model parallelism. What I mean here is that mostly in machine learning, people just split their batches on different ranks, and that's the data parallelism to train the network in parallel. What we need is a model parallelism, because for us, every step, like the grid for the simulation needs to be split up across different ranks. It's possible to do now that in mesh TensorFlow. I will not go into the technical details of how it does it, because that's not the point of the talk. But essentially what it does is you define a mesh, which is basically n processors that you want to chain together and a dimension for them. You rewrite your TensorFlow API to basically make logical tensors. So for every dimension of the tensor, you name the dimension, and then you define a computational layout. So you say which tensor dimension needs to be split on which mesh dimension. So for example, here I have split my X height dimension in like 4 processes, and I have not split my width dimension. The challenge here is the challenge that you have for any PM simulation when you're scaling it up to multiprocessing and like the large scales. So what I'm showing here, and that is the 3D fast Fourier transforms. So what I'm showing here is essentially the time graph, time pie chart for the hidden valley simulation that we ran. So this is 2560 simulation and a 10,000 cube simulation that we ran on Cori. And you see that in both the cases, more than 50% of the time is taken simply by 3D FFTs, which makes sense because 3D FFTs essentially require communication from all to all. So you are essentially every rank, the data is transferring from all ranks to all ranks in this case. This is much more severe in mesh TensorFlow because it's a new framework and they do not have optimized FFTs yet. So one way to get around that is to what people have tried to do before is essentially use a multi-grid scheme where you split your scales to calculate the force. So you use a coarse resolution simulation to do the large scale forces, and you use a finer grid to get the small scale forces. What we are exploring right now is to implement such a scheme with a novel method called Laplacian image pyramids. So this is fairly known in image processing world. What it essentially does very briefly is, say you have an image, you recursively smooth and blur it, you recursively blur it and downsample it to generate something which is called Gaussian pyramid, because mostly people use the Gaussian blurring for this. And then what you can do is for every level of the pyramid, you can upsample it and calculate the difference with the original for that level to get this details component, or like the residual component. And then the hierarchy of this residual component is called the Laplacian pyramid. And if you have the full hierarchy as well as the final image that you have, then you can just upsample it and add the details component to reconstruct the original without any loss. So it's perfect reconstruction in this sense. So what we did in this preliminary work is essentially generate a 2-level Laplacian pyramid where you use bispline kernel for smoothing, or bispline kernel for smoothing your final field, and a convolution which is super efficient in TensorFlow with strides of 2D to do the downsampling. This is a super preliminary result with that. So what I'm showing here is a simulation for 5-step fast PM on a 200 megaparsec box. The original was 128 cube grid. So this is what it looks like when you run it on a single process. So no parallelization. This is what we did with like a 2 process where we split our mesh along the x-axis, and the low mesh resolution was 32 cube. So in this case, the communication for the FFT is done on 32 cube instead of 128 cube. So that brings it down by a factor of 4 cube in terms of data volume. And what I'm showing here is the transfer function and cross correlation between these two, the reference simulation and the pyramid simulation. So we get sub% accuracy, at least on this test case. But yeah, this is super preliminary. We need to test how it scales and how much it benefit, how much we gain in terms of time with respect to it, and how it compares with other CP implementations. So those are the things to be looked at, but this is the summary, and I'll move on. Thanks.
Yes, Alan.
You would have had an implementation for reconstructing the initial mode.
Yep.
So what you told us the absolute
The gain for the single process implementation, it's pretty much as fast as the CPU implementation. So because of the GPU optimization, if you're just comparing the forward modeling with the fast PM simulation and the flow PM thing, on a single process, flow PM is faster. But that's because GPUs are more optimized than the thing. Things break, like it becomes much slower once you go for the parallel thing. But for the reconstruction, I think the gain is like 2x in terms of a single process implementation. Yeah.
Andrew?
Sorry? No, not yet. But I mean, in principle, all the operators are pretty much the same, right? So yeah, so it should, other than more coding and more manpower, I don't think much. But yeah, but then at the same time, the thing that we are also thinking about doing is use some approach like what BW was talking about yesterday, in that now it is in TensorFlow, so you can probably use some deep learning components to learn those effect for the baryons and other things. So depending on which, yeah, or what your outlook is, you can use a simple parameterized model, or you can actually code the entire thing, or you can use deep learning models. So that's a matter of perspective. But in terms of coding, I think it, yeah, it should be straightforward to extend this to other kind of simulations, which is why I showed the numerical scheme saying that you can like just use the tools here to build your own favorite forward model out of this.
Other questions? If not, let's thank the speaker again. Okay, so next we have Mariana Vargas Macania talking about Decimap challenges.
Yeah, it's fine. So, well, this is pretty much a work that is, we are coordinating. Albert, that is there with the working group leads of DESI, that Hee-Young is there, and Florian. So I'm gonna present the status and the plans for the short term. So for those that are not in DESI, I'm gonna start with a very brief framework where this is being built, and then I go directly to the status of this mock challenge. So we have basically 3 documents that are guiding us for constructing this mock challenge. The first one of them is the science readiness plan that is listing all the steps that we need to accomplish in order to extract all the information from the DESI survey. Then we develop, within these 2 years from now, a couple of documents that are kind of guiding us in the sense that the first document is describing the set of simulations that we need to test the observables that we're going to use in DESI, in particular BAO and RSD focus. And then there is a document that is basically led by Lagos and Musha, where there is a description of all the systematics that we're going to test, and what are the simulations that we require for test them. And then even the metrics are highlighted there. So these are the basis of the discussions. I just point out some of the dates that were in these documents. So you cannot see from there maybe, but if you see the documents, you will see that most of them are pointing out to sometime in the last year. So for having these simulations or even to start testing these systematics. So the idea of today is to present a little bit of where we are in this planning. What is the goal of this mock challenge? So we have basically 3 goals. The first goal is we have within the collaboration bunch of codes for doing large scale structure analysis, but we need to cross-validate all of them. So this is the first goal. The second goal is with the philosophy of DESI. The idea of DESI is to have a fiducial DESI pipeline for doing large scale structure, in particular for extracting information for the BAO and RSD. So an output of this exercise of the mock challenge should be to have a fiducial pipeline for performing large scale structure analysis, at least the standard analysis. And finally, the third goal of this exercise is also to get a first assessment of the error for DESI. So what I'm talking about pipeline, I'm thinking this like a different set of modules. So we have the measurements pipeline that is here. I'm not going to talk about today just 2 slides about the observational systematics, but it's also included in this pipeline. And we also have this part of the features, like the 2 observables that we need to, that we are going to analyze in DESI, the BAO feature and the RSD feature. And then we have this covariance module that we also want to test. In parallel with this, for example, for the BAO feature, one of the things that we want to test also is the reconstruction, as it is kind of part of the standard analysis. So we want to cover with the mock challenge all these different modules. So from the document that I just presented, there is a list of all the mock challenge that we want to pursue before the data arrives. And we have the measurements, the covariance, the features, the reconstruction, the observational systematics, separating the photometry and the spectroscopy, and then all the other mock challenges that are related with the full shape analysis, but not RSD analysis. And finally, also the inference module. So this is the plan. And what we have started to do since last semester is like this block that is here that I'm gonna describe. And then I'm gonna pass in the second part to describe what are the plans for the next semester. And pretty much of the second semester is work in progress. So you need to take it with a grain of salt. And that is what we are not going to do the next semester, but we plan to do sometime later. So the measurements mock challenge started in August last year. And we start this challenge and we called for volunteers for participating. And we have about 23 participants, so about 15 to 14 different codes for the measurements. The idea of this first measurement challenge was just to contrast the different codes available for the measurement. It could be very simple, but even at this level, we need to agree in the precision of the machine of all these different estimators. So for this first comparison of the measurement, we use 2 simulations, but I'm gonna be describing just unit simulation because it's the one that we are using for the further stages of the measurements challenge. So these unit simulations are per initial condition with fixed amplitude. I think someone already described this pretty well. This is a gigaparsec box, and this is the particle mass. So why we are using these simulations is because in the short term, that was the simulation that it was providing us with this technique of suppression variance, the precision at the DESI level that we require, and we have also the resolution to resolve ELGs. That was one of the drivers of these comparisons. So for the first stage of the mock challenge, we just tested in periodic boxes. So in this case, the answer is analytic. So we should have all the comparisons at the precision of matching precision. And there is not like very exciting results in this first part, but it took us several iterations to all the different groups to converge to the right results. So I'm not gonna present the plot for this part, but one of the things that we learned for the first exercise was just to let the logistics of this mock challenge. In the second stage was more interesting, And the idea was, in this case, we provide a simulation without redshift evolution, just using a single snapshot with cut sky geometry. And then the idea is it becomes more interesting because there are some choices of the different people groups that are related with the line of sight or with the window function. In the case of the Fourier space, the weighted data. Again, after a few iterations, we have some of the learned lessons from this exercise. So here we have the Fourier space, the configuration space, the different multiples. We requested the even and the odd multiples. The even just because it allows us to look for systematics and things like that. So we also want to make sure that they agree at a certain level. So you cannot see the numbers from there, but the idea is that we achieve a very good match within the different groups codes and in the configuration space also. One of the two lessons is just to make sure that to convince you that this exercise is important is from this comparison, we corrected some of the codes. For example, Alex corrected the embodied kit when that was one of the outputs of this comparison of codes. Also, we learned that within the collaboration, we have two different conventions for the estimator in the Fourier space that give different results for the hexadecapod, but when using the same convention, everything agrees at the right level. So the stage 3 just started after the stage 2, and the deadline was this December. So it's the first iteration starting this January. We don't have yet the consensus of all the measurements, but this is just the preliminary results. These are the few groups that just get to the stage 3 of the measurements, but we hope to get more people in this last part of the measurement challenge. But the idea of that will be that after this exercise, we will have all the calls cross-validated, and we will be able to go to the next stage. So from next stage is we are going to go to the fitter part. So, but for performing a fit, we need the covariance. And one of the points that were discussed since Ohio meeting was the covariance challenge. So this is something that is pretty much under discussion now. There is a plan that is mostly set up by Albert that is in the audience. I'm gonna go very briefly about it because I want to go to the BAO and Reconstruction. The idea, we have already all this bunch of people that want to participate. The idea is also to have these different stages, boxes, sky cuts with single snapshot and then with redshift evolution. And then these are the set of simulations that we have available now. This is kind of the limiting part of this mock challenge that we want to develop this for this semester. And what we have decided, we haven't decided so far, but what is under discussion is we are going to use a suite of simulations that is kind of available now. It's small boxes, and we are going to compare in these small boxes different kind of simulations, and we are going to compare this with some analytical models. And what it comes from this exercise, where we are planning to use SLICs, that is this volume, and compare with FastPM and EasyMox, and with some analytical methods of the people that want to participate. And we are going to try to get from this exercise a covariance matrix that will be rescaled for use to be used for the fitter part. So there are some trade-offs that we know that we have. So as I mentioned before, one of the driver of this exercise is that need to be done now. So we need to use whatever is available or whatever is feasible to run in the short term. So that's what is driving our choices for now. We have 2 stages planned for the BAO part. For the first part, as we didn't have any covariance available yet, what was proposed in December was to start with some data, vector, and covariance provided, generated from models directly. So it's Nikhil leading this effort. He's preparing the covariance, Gaussian covariance, and then preparing the data vectors also from models. And the idea is to provide this to the participants and to try to start to set up the filters for this second stage of the mock challenge. So this is already on the wiki, but the outputs, the inputs for this exercise are not ready yet, but hopefully in a week or something like that, we can provide that, and we are gonna start the challenge. So these are the elements that I just described. We're going to provide 2 covariants and 2 data vectors, and the idea of the people will be to provide the BAO parameters with the errors, and we are going to compare these 2 with the different groups. So the idea of a stage 2 is that it comes exactly after the covariance matrix challenge. The idea is to use whatever simulations we have available now, embodied simulations, and then use the covariance matrix that we are just getting from this covariant challenge. And then for now, this is completely also under discussion, so nothing settled yet. The idea is to use UNIT and Crow Canyon probably for these filters, provide the covariance coming from this covariant challenge, and then try to compare the different metrics, again, the deviation from the central values and the comparison of the errors using all the same inputs for everybody. This is the kind of output that we want to get from this exercise. So here you cannot see, for you have the BAO parameters and the growth factor parameters, F sigma A. So one of the things that I didn't mention is that when we were thinking in proposing this BAO challenge, we are fixing one of the parts of the analysis, that is the reconstruction, because the idea, at least for now, is to separate the BAO filter of the reconstruction and then to test the reconstruction by itself. We have heard already in this session, there are a bunch of codes, new codes, in particular non-standard methods that haven't been applied to data. So the idea of this challenge is to check which ones of these methods are ready for being used to DESI. So that they include all these RSD, survey mask, allo galaxy bias, and chat noise. And then to check if they are also have the performance that allow us to implement that in DESI, like simulations. So the idea is to use the same simulation as before, UNIT and Crow Canyon. And again, these different stages, boxes, cut sky without redshift evolution, cut sky with redshift evolution. And the timeline is kind of still a little bit flu, but the idea is if we think this mouse could be ready by mid-February, and we think that by mid-February we can have first covariance matrix to work with, so we can start this already, this challenge. What we want to test for reconstruction, so there are different metrics. You have seen many of them already in the previous sessions. So the displacement field correlations, the propagators, like the correlation with the initial conditions, the 2-point and 3-point statistics. And then also we want to test the BAO fits performance once we fix the covariance and the BAO filter in the analysis. I don't know if something else could be added, but I think with that we already cover a full range of metrics. So these are the examples, but you already seen in previous talks what are the things that we like to test in reconstruction codes. So finally, it's just an advertisement that this is not official part of the mock challenge, but there is also an effort within DESI collaboration that is mostly led by Ashley Ross. And there is a lot of people participating, but in particular, Charlotte is working, Mary, Kiyon, and Lalo. And the idea is to test how the mitigation techniques and the observational systematics affect the BAO and RSD observables. For that, they are using easy mocks with and without photometric systematics for now. They are looking for chips in the BAO. It's just, this is still work in progress. There are very, very, very preliminary results I'm gonna show, but it's just an example. It's not conclusive. Just the mocks with and without systematics, and the first fits that we are performing without any mitigation, correction, are giving non-biased results. So we really expect that once we also include these mitigation techniques, it's gonna be even better, this part. Okay, so final thought is, I want to insist on that we are doing with, we want to push this mock challenge this semester before data arrives. The limiting part is the mock challenge, so we are doing with the best mocks that we can have, like in the short term, to progress on this task. Well, I think the output of this exercise, even if we don't go that further, is going to be like homogenize the different codes within the collaboration. In particular, all these different parts that I already mentioned, the measurements, covariance, filters, and reconstruction. That is something that haven't done so far. So I think is required. And this is a question that people just asked me yesterday, if this challenge will be open to people outside the collaboration. This is something that I don't think I can answer, but I think we can discuss it in the collaboration. It's in the interest of the collaboration to include more models probably, or things like that. But this is something that needs to be discussed within the collaboration. I think that's all for me. Thanks.
Questions?
Can you say a little bit more about what approaches you could use for the covariance matrix, and is there a particular focus in terms of the scale or the all scales?
Are you referring to analytical methods?
Just the covariance challenge.
In fact, it's gonna depend on people participating in the challenge. So basically, I think I think there are some public codes, but we don't have people within the collaboration that probably is gonna participate in the challenge using those codes. So we need to look for people to use that codes or something, but for now we have like limited amount of people participating in the model mock challenge. But we haven't announced it yet like that much, so we need to check. But it will be good to have a first idea of how many people we are going to participate. Also for the reconstruction code is the same. I don't know how many people is gonna participate.
I think the main point of the challenge is to figure out at what scales we need more number of scales we use analytical.
Other questions? If not, I think let's thank the speaker again.